if you differentiate one parameter groups emanating from this product, then the canonical commutation relations just jump out. That's so. And the whole purpose why I did this was due to that fact. Now, what norm shall we use to on this group algebra of Hx? This enlargement of H. One looks at representations into the bounded operators of the given Hilbert space, and then one takes the norm of the element, the norm of the bounded operator, that's in the Hilbert space, that's meant by this 0, and then one takes the supremum that exists, okay, and that's then the norm. That's a well-known norm. That makes the matter rather convenient. This norm, which was constructed here for the Heisenberg group algebra, we can also take over almost like Barton to the Weil algebra, and now complete them, and we get, of course, C-star algebras. Those are the C-star algebras of the vector field effect. Here, this is used to quantize it. Here, this part will be used to deform this quantization and go down to h. We do it by, we get then the limit as h bar goes to 0, exactly as you did. In a way, Basil, I make an example of yours. But not...
An example of me, or...?
Yeah, exactly. Let me say so, an example of yours. Of course, if you stop at the engagement, there is that beautiful for us. We learn very much way of getting through this very big mathematical scene. But of course, not in that broad form. The example is not in that broad form, it is just an example. I'm sure it can be brought into the connections, into the direct connections. The C-star algebra, the Weil algebra, and the Heisenberg C-star algebra are related by taking an arbitrary element in here, say a generating element that is made up by a section, into the Heisenberg group bundle and that specific center element. Then we take the Weil element of the section part and put in front of it this phase factor. What it does is, here we have these extras, and of course these extras are now directly linked with this delta function type, these linear functions defined by the delta functions. So the center part determined by this element E, the unit element of the quaternions, of course, that is winded along the circle operating on such elements. That's a suggestion. Now, what did I have more? Ah, yeah. Now, the quantization is made in two steps. In a sort of a pre-quantization, by giving a Poisson algebra, taking the Poisson algebra in a star algebra, and then taking a representation of that Poisson algebra. And those are then the physical objects. The Poisson algebra is made as follows. We can multiply the symplectic structure we have with any fixed number. That means only we make the vector a bit longer or a bit smaller. But all the vectors along the line in the same fashion. Taking the length 0 makes that symplectic structure vanish. Because this is a very degenerate, idiotic sort of Heisenberg algebra bundles. The Heisenberg algebras are, from the algebraic point of view, completely trivial, totally degenerate. But the symplectic structure sneaks in backwards by the brackets defined as here. Again, the sum, the Weil element of the sum. In this case, of course, since the symplectic structure is 0, the phase factor is identical to 1. But the symplectic structure comes in here again. So the non-commutativity enters by the symplectic structure again. But that's the Poisson algebra structure. And also that Poisson algebra determines the vector field up to equivalence. Now, we look at the different Weil algebras we can do by multiplying elements in R by, with the symplectic structure coming from the vector field A. Remember, having 0 yields the Poisson algebra. Taking it off of 0 gives a known C star algebra for that vector field X. Now we have many C star algebras. And what we do is we take here actually the C star Weil algebras, I should have written here the C star. For each H varying in R, that's a trivial bundle, and now we take again sections. The sections have now to be chosen a bit more carefully to make a new C star algebras of these sections. That means functions into this, from R into this, into VXH bar, since this bundle here is trivial. But the only way you can do it is to get a C star algebra which is isomorphic to the C star Heisenberg group algebra. And that's called a Weil field. That's what we talked yesterday about. And of course, since we have functions here from R into elements of that thing here, we have the point evaluation. We can take a function defined on the points of R, values in here. We can take a particular point and evaluate that, the value of that function at that point and get a specific value. Of course, we enter then the Weil field. And that's also a search action. Now, let me go to the quantization and prepare the whole quantization. We take the Poisson algebra, take a quantization map, and the quantization map associates to a section of the Heisenberg group bundle to such a function. H goes over to the Weil element, but stretched by the factor H. Of course, that constant now can be chosen such that it is Planck's constant. And now we do the following. We go in this field of C star, this field, C star algebra coming from Weil fields. Take then, so we represent this and then take the point evaluation and get, of course, here a quantization from the P into that H.